Welcome everyone, and this is part B of section 16.6. We are going to see an example here. Find a vector function that represents the plane that passes through the point P sub 0 with position vector R0 and that contains two non-parallel vectors A and B. So we are finding the equation of a plane that passes through a point P0, that's shown here in the picture like that, whose position vector is R0, and it also contains two non-parallel vectors A and B. So first we are going to find out a parametric representation of a plane. You know that plane is after all a surface. The surface parametric representation would mean writing the plane in terms of two variables, say u and v. The first, in order to reach the point P from P0, we can move along the direction of A, some units, and then in the direction of B, certain units. So from P0, you can start along the direction of A because the plane contains the two non-parallel vectors A and B. Wherever they are in that plane, you can move them by using the representations of the vector. You can move them so that it starts at the initial point to have the initial point at P0. So the two non-parallel vectors are moved to the position P0. P0 is a point on the plane with position vector R0. So in order to go from P0 to P, you walk along certain units in A direction and you walk along the direction of B, certain number of units to reach P. So if I call the vector R, so P0P vector can be written as UA plus VB, where U and V are scalars. Then we are going to find out the position vector R for the point P. So if I consider, let R be the position vector of the point P. So what is R? The vector R is the position vector of P0 and the P0 to P, right? By parallelogram law. By parallelogram law. So R equal to, which is the position vector of the point P, is OP0 plus P0P. But what is OP0? OP0 is given to have the position vector R0. The point P0 has a position vector R0, which is given in the problem. So R0 plus P0P, P0P from what we have written earlier is UA plus VP. So we can write R of the parameter U and V equal to R0 plus UA plus VB, which is the parametric representation of the surface or representation of the plane in this case, plane having a point P0 with the position vector R0 and have and having two non-parallel vectors, vectors A and B. This is the parametric representation. Now, from the parametric representation, we can always find out the parametric equations of the surface. So let's assume that let R has coordinates, let's say X, Y, Z, and let A have coordinates A1, A2, A3, or the components of the vector A as A1, A2, A3. And if B has components B1, B2, B3, then substituting back into 1, we get XYZ equal to X0, Y0, Z0, which are the position vector, the components of R0, n plus U times A1, A2, A3 in component form, V times B1, B2, B3 in component form. So from here, this is the parametric equation of the plane. Now, what we are going to write is the parametric equations of the plane. Parametric equations of this plane, this particular plane with the conditions given. So I equate the coordinates x on either side. X component on the left hand side is x. X component on the right hand side would be x0 plus ua1 plus vb1. Y is y0 plus ua2 plus vb2. Z is z0 plus ua3 plus vb3. These are parametric equations of this particular plane. There is a problem here, problem number 19, which is based off this equation that we derived, equation of a plane passing through a point and having two non-parallel vectors. This problem number 19 is done in the section video. Please refer to the videos for this section on 16.6 for this particular problem. Now let's find out the parametric equation of the sphere. Find the parametric equation of the sphere x square plus y square plus z square equal to a square. Earlier we saw parametric, we have actually done spherical coordinates earlier, where we know that the spherical coordinates can be written as rho, phi, and theta, where rho in particular is rho is the radius of the sphere. So we can use spherical coordinates here. Spherical coordinates that we did earlier are rho, phi, theta. And we know that rho stands for the radius. And theta runs from 0 to 2 pi. And phi runs from 0 to pi. We have done that in spherical coordinate section in chapter 15. The only difference here is we are going to use, in order to represent a surface, in particular here sphere, we need two parameters. We have to come up with those two parameters to represent the sphere. So one is kind of fixed here. Here the radius of the sphere is going to be A. So rho in this particular case happens to be A. So if that is fixed, we can choose phi and theta to be our parameters to represent the sphere. So keeping that in mind, we can write x in spherical coordinates, we write that as rho sine phi cosine theta. Here it is a sine phi cosine theta. Y can be written as a sine phi sine theta. Z can be written as, in spherical coordinates, it's rho cosine phi. Here it is a cosine phi, because here the radius rho equal to a. So we actually represented a sphere in terms of the parameters phi and theta. So the parametric representation of the sphere would be is r, vector r. It is in terms of phi and theta, which is equal to xi plus yj plus zk, where x is a sine phi cosine theta I plus a sine phi sine theta j, which is the y. Then z is a cosine phi, that is the z component. So we can write like this. Here the understanding is that phi is between 0 and pi, and theta is from 0 to 2 pi. So here, when you say phi is a constant, it actually means that it means these are circles of constant latitude. So phi equal to constant are circles of constant latitude. This includes equator as well. And theta equal to constant are meridians, are semicircles which connect north and the south poles. As shown in this figure. You have actually seen the interpretation of phi equal to constant in spherical coordinates, representing either the upper cone or the lower cone, and then theta equal to constant in spherical coordinates will mean a vertical plane. In this case, in sphere, they are circles of constant latitude. They are phi equal to constant, and theta equal to constant will mean they are meridians connecting the North Pole and the South Pole. Let's now see an expression for the tangent plane to a surface in parametric form. How do we represent the tangent plane to a surface in parametric form? We now find the tangent plane to a parametric surface as traced out by a vector function r of uv, which is x of uvi plus y of uvj plus z of uvk at a point p0 with position vector r of u0 v0. So we have a surface in parametric form, is the surface, and we have a point in that surface which is represented by the position vector r of u0 v0. And then we need to find out the equation of the tangent plane. For that we need r of u, because whenever we write an equation of a plane, we need the normal vector. So we are determining what normal vector we can consider for this tangent plane. So r sub u is given by, you are differentiating r with respect to u. That means you are differentiating this equation with respect to u partially. So it can be written as dou x by partial derivative of x with respect to u, I, plus partial derivative of y with respect to u, j, plus partial derivative of u of z with respect to u, k. Now, are we same way, we are differentiating equation 1 r of u v partially with respect to v. So it will be dou x by dou v I plus dou y by dou v j plus dou z by dou v k. If R of uv cross rv or u cross rv is not zero, the cross product is not zero, then the surface is called a smooth surface. It has no corners. For a smooth surface, the tangent plane is the plane that contains the tangent vectors Ru and Rv. It contains the tangent vectors Ru and Rv. And the vector Ru cross Rv is a vector normal to this tangent plane, is a normal vector. So the idea is that so whenever you want to find out the equation of the tangent plane, um, if they give you what the point P0 is, you can find out, you can keep that point P0. If they give you a specific parameter for that point P0, you can plug in that parameter and get the point. Then you need the normal vector. The normal vector is provided by Ru cross Rv. The components of Ru cross Rv will be will, you can actually find out the equation in the form a times x minus x0, b times y minus y0, plus c times z minus z0 equal to 0. X0, Y0, Z0 comes through the point P0 that you got here. And then A, B, C are the components of the normal vector. So you can write A, B, C as a normal vector. They are the components of RU cross RV. Then it becomes easy to write down the equation of the tangent plane. So this problem number 35 is based on this idea, finding the equation of the tangent plane. This problem you find in the videos for this section. So refer to the videos for this section 16.6. I will be continuing with this material, the concept of section 16.6 in part C of the video. Please check part C of this concept video for section 16.6 for the rest of the material.